Hello everyone, welcome back to the class, and we'd like to start our first lecture. As I mentioned earlier, in semester 1 we will cover part 1 and 2, that is global and local strengths. So in total 9 topics will be covered in part 1, and after that we will have another 6 topics in part 2. Today's topic is here simple beam theory, and let's have a look at the details. So briefly, today I'd like to remind the things that we have covered in last semester by Marine Mechanics MAR 109. So for the Hurlgotha analysis, from here the meaning of Hurlgotha analysis is global analysis, and we should be able to utilize the basic fundamentals, laws of mechanics, and marine mechanics, statics, dynamics, as well as solid mechanics, mathematics, and we should be able to simplify the given problems. So here, as you can see, this is the beam structure. Beam is here, beam, and the given load is here as well. So it's up to them. Applied loading type, they can decide it. In the case of boundary condition, they can decide it as well. In the case of ship structures, and this is ship, and we have the buoyancy force and weight distribution. Based on that, we could be able to calculate the shear force distribution. From here, we can get bending moment diagram, bending moment distribution as well. And the next step was from here, the obtained bending moment diagram, we could find the maximum bending moment, the position, and then we can calculate further. After that, we should be able to check the material yield stress or the capacity, so that we can compare those things and the material part, so that we could be able to calculate safety factor. That was the previous learning. So here, beam again. My definition in last semester, that was the slender structure here. Slender is like this, and then subjected to the bending moment. That was the definition of beam. And we also have learned about the column, beam column, rod, something like that. So here they are talking about a structural member carries lateral load along its longitudinal axis. So here, as we can see, the definition, the important keyword is bending and one dimension. This represents slender structure. So as you can see here, this is beam, and we can also see the types of loading: concentrated or the distributed. And this is beam structure. This is sectional properties. So that was the beam, and ship models as a beam. You know what I'm saying here? So this is the typical section of the ship structure. It looks like the double hull here, double hull oil tanker. It looks like VLCC or ULCC. All right. So of course, as we see the previous the video, they said the ship structure could be considered as the simple beam structures. So here, this is the captured video, or you can click this YouTube clip, and you can spend less than 2-3 minutes. You can understand what I'm talking about. Please have a look. And here, this is, apart from our lecture, this should be considered as very important thing as a ship structural engineers. So this is typical shape, typical design of the oil tanker. It looks like Suezmax class double hull oil tanker. And if you see here, basically they provide two important informations is related to geometry and material properties. So geometry is given here and material properties are here. So this is length information and breadth and depth, and FS represent, this is not the factor of safety, this represent frame spacing. Frame means like this. This is one frame, and if we see here, this is ship structure and consists of like 5 to 9 hold. So one hold has 5 to 6 frame spacings, frames. So you can understand what I'm talking about. One frame is like 4 to 6 meters. Okay, so one frame spacing is 4.12 meter in this case. And all the geometric information is here, build scale and the length, and material properties are given here as well. AH and mild steel here. If I'm not mistaken, we had discussed about this earlier, mild steel and AH. If you don't remember, the mild steel 24 was 24 kilogram force times gravity 9.81, so that you can get 235, nearly 235 megapascal. And the AH is same as high tensile 32 is 32 times 9.81 is nearly 313 or 315 megapascal. So those values represent material capacity. What I'm talking about is yield strength. So this is the given information and why they are talking about this. So from that, we can simplify the structure from here to here. So the question again, this ship models as a beam, whether it is possible or not. Why not? As you can see here, all those structure members can be splitted into beam structures. This is beam. You know what I'm saying? And in our case, we called plate, stiffener, combination model. So we called PSC, or we can split it based on the plate and stiffener and plate. This is like beam, but this is plate and stiffener separation model, PSS. You don't need to remember these, but what we are talking about is here now. PSC. So that can be considered as the beam. So what is bending? So every single beam element you can see here, the deck or the inner bottom, side shell and outer bottom, that can be considered as the fiber, and that is subjected to the pure bending moment here. This is neutral axis. So from that, we can calculate the strain values, a measure of deformation of the material in 1D slender structures according to the small displacement theory. So from here, this strain value is changes in length and original length. We have learned this before. So about this kind of the bending, so we could be able to obtain this one before, and If you don't remember, please have a look, remind it, and please open the previous lecture slide, and I have provided this one before for you to drive this kind of simple beam theory, right? And this is the stress. We learned about the Hooke stress before, Hooke's law, and the elastic materials. So this is Hooke's law, and we will combine these strain values. So we could be able to combine those two so that we could get this relationship. All right, this is the stress curvature relationship, and internal force in longitudinal direction. And the important thing here is here at centroid, the cross section, the integration value, the force should be 0. You know what I'm saying? So previously we learned that once we have this kind of beam structures subjected to bending moment, this is actually sagging bending moment, so that this section we can see here, it will be compressed at deck, and at bottom part it will be tensioned. This is compression, out the bottom is tension. This is actually the outcome of the simple beam theory. But here what I'm talking about is at neutral axis we don't experience any type of the force, which means that the force value at neutral axis is always 0. So that is utilized here. And I'm asking you here 3 different types of the geometry and neutral axis given here, like type 1, 2, and 3. And as you can see here, at here, neutral axis position, the force should be 0. So distribution of the stress will be like this. Sorry. At here, that should be 0. And it will be like this. This is also 0. Also 0. Okay. So question, in this case, can you find the position of neutral axis? I think I have asked this question in the exam. So basically you can think that, oh, it's like B because it's located at the center. But as you can see here, this is double bottom structures. So we have more weight here, more area here, which means that the neutral axis should be shifted to the bottom part. So I think the answer should be like this, right? So internal bending moment, from that assumptions we could be able to drive further, and second, moment of inertia I, so that we could be able to simplify it, so that previously we could be able to drive this one, and we called this as the bending stress or flexure formula. So bending stress is apply the moment times the distance. Here, this is the distance. Distance means this is the section, this is neutral axis. So from the neutral axis, we can calculate the distance y, okay, over moment of inertia I. This is bending stress. So after that, we will compare those values with material yield so that we can get a safety factor. Okay. So we learned this before and simple beam theory, and basically what we need is the final, and then this should be highlighted as well. So in this case, this is pure bending moment. M is applied. This is actually hogging bending moment. And can you imagine? Can you predict the stress distribution? What we learned is this one before, the C. We learned C before, and C was, the answer should be C, but how about D? From here, you should be able to think about shear problems, right? Always maximum shear will be occurred at neutral axis. That's why the web is functioning to cover shear, but the flange here, the maximum stress will be covered by the flange. So that is bending. That was the question in the exam for MAR 109 as well. So you should be able to understand these basic informations. All-over stress design, and as I mentioned earlier, capacity must be better than demand. In this case, capacity means bending stress. The capacity must be better than demand, and this is bending stress, and our capacity is from material. So our material property, material capacity must be better than bending stress. So this is the concept of the allowable stress design. So in this case, we could utilize moment y over I. This is flexure formula, and this is come from material. So from this simple comparison, we can calculate the safety factor, whether it is safe or not. Okay, and here we can simplify it further. It's like m over jet. This jet here, this section modulus represent jet is I over y. So what will be the unit? In the case of I, this is meter out to the 4 or millimeter 4. And the y is distance, m or millimeter. So here, this jet unit should be meter cube or millimeter cube. This is for your information. So here they are talking about the local effect from M moment and cross-sectional properties, section modulus, so that we can get bending stress. And this is constraint. This is from the material yield. So as a structural engineer, structural designer, we can decide it whether we should change our geometry or we can select different material. All right. So question again, location of the maximum stress. So this is the neutral axis, and what we have learned is the bending stress is my over I. So in the case of I, this I come from this section. So this is constant, and apply the moment, constant. So what we need to think is y value. So in the case of deck, this is distance to the deck. This is distance to the outer bottom. Of course, this length is, longer than this. So in the case of stress level, you can think about it. substitute it, I and M constant, and you can think which one will be higher. All right, or you can see the answer here. This is the stress distribution obtained from the finite element method, and basically they have applied the bending moment. If I'm not mistaken, they have applied the sagging bending moment. So as you can see here, the positive value represented by the red color here, 124 megapascal, and here this is compression applied from the sagging bending moment. So that will be compressed. So this is negative 168 something megapascal. So as you can see here, the value applied, the stress value is this one is higher than here. So which means that it will be like this. This is 168. This is 124. Can you understand? So you can see this question again, location of the maximum stress. Okay. And beam deflection, this is simple beam theory again. So please have a look again how to drive this equation, curvature and moment curvature relationship. And here we have learned it before. Please drive it. And load shear force moment relationship. I have highlighted more than enough times, and from the deflection, slope, moment, shear, and load, if we know one value, we could get all the details by applying the boundary conditions. We could decide the unknown coefficient. So everything is same here. What they are talking about is shear, moment, slope, deflection. Okay. And sign convention, we have defined sign convention before. Positive shear and positive bending moment represented here. So what was the procedure? First of all, we need to calculate the buoyancy and the weight distribution and integrate it so that we can get shear force distribution, integration again, bending moment, and we can design the section such that here this is bending stress actually. Again, this part represents bending stress is my over I. Z was same as I over y, and this is come from material yield. It's like stress and strain, and we conduct the test, tensile test, and this part we could define this is yield stress, right? So that was the procedure, and that's all today, and thank you very much. And if you have any question on simple beam theory, you can leave a message or email me. Thank you very much, and next class we will cover here the ships in still water, topic 2, and topic 3 will be the waves. Thanks very much.